All right. So let me just wrap this up for you quickly, and then we will take a look at how we can deal with this kind of partial differential equations. Okay, so we said that we looked for a steady state solution. What is a steady state solution? It is when the time goes to infinity and the change with respect to time settles down, and therefore you basically have no variation with respect to time. But since this is a partial differential equation, the solution still has a dependence on x. Okay, and we have seen that we have a linear dependence on x with two I wouldn't say constants, but basically I have two parameters, c1 and c2, which are still not determined, and we also said that you would find them by using the boundary conditions. Okay, so let's also quickly do that. Okay, the boundary conditions. So boundary conditions would give us simply at x is equal to 0, the left hand side, I have t steady state at x is equal to 0 is basically equal to, you can see that in this case you assign x as being equal to 0 in that formula. So that is, we can call this T0SS, and that's going to be our C2, okay, because the first term vanishes from that equation. And similarly, at x is equal to L, now you have steady state at L, which we can also call TLSS. Okay, that's going to be C1 times L plus C2, and that is equal to C1 times L plus T0SS. Okay, and therefore we have C1 being just equal to TLSS minus T0SS simply divided by L. Okay, so that's your other unknown. Okay, so these are constants because at this point both the time variable has vanished and also the space variable has vanished. So these are two constants, and what you get in return is that your steady state solution at x is basically your steady state solution at point 0 plus simply a slope. Okay, TLSS minus T0SS divided by L, which is the slope times x. So that's your steady state solution. So the steady state solution is still a function, and it's a function of x, obviously. The time variable no longer exists. So depending on what are the initial, what are the boundary conditions, obviously, you basically have a linear function of x. So let's say this is x is equal to 0, then, and this is x is equal to L. We have a boundary condition over here, which is T0SS. And you have another boundary condition over there. Let's say this is 0. Okay, that will not necessarily be 0, so let's put it something non-zero. This is TLSS, another constant. So in between these two, you will have a linear relationship. Okay. So that is kind of something that is intuitive, because if you think about it, as time goes to infinity and all the transients die out, what will happen is that your rod, which is insulated from the sides, will have one end and one boundary condition, and the other end at the other boundary condition, and there will be just a uniform distribution of temperatures inside from left to right. Okay, so that is our steady state solution. Okay, now So how do we approach when we have a system like this? So question is, how do we design controllers for such meaning distributed systems? Okay. Now that is discussed in again one of our reference books, which is Fikar's book. Okay. What is described there is that there are two approaches. One is called the late pass, and the other one is called the early pass. Okay. Now, a late pass is that you try to use the partial differential equation directly to design controllers. Okay, and eventually you will need to use some kind of a numerical approach. Okay, use a numerical solution as a final step. Okay, now that's going to be beyond our scope because that really requires kind of advanced control theory for distributed systems. Okay, requires advanced control theory for distributed systems. Now, what we will rather focus is the approach called the early pass method. The early pass, what it does is that rather it just discretizes the space variable. Okay, so this discretizes the space variable at the beginning. So as a first step, it basically eliminates the distributed kind of nature of the problem. Okay, and obtain, and we will discuss what it means to discretize the space variable, obtain a higher order lumped parameter model. Okay. Now this is also called, it has quite a popular name. This is called the finite element method. Okay. Finite element method. Okay. By the way, I started looking at your classic questions in the exam. I hope to kind of grade them soon. But one thing I have noticed in the first question is that you guys have a confusion about the order of a system. Okay, for a nonlinear system, which the first question had, a nonlinear system, basically the number of state equations that you can write, that means the number of first order differential equations that you can write, which are our state equations, determine the order of the system. Okay, the order of the system over there was 2 because you were able to write, there were 2 tanks, and for each one of them you were able to write one first order differential equation. Okay, this is not related with linearization. In fact, linearization was not necessary there. Okay, and was not asked actually, but you were able to write 2 first order nonlinear differential equations. So the order of the system was 2, and you needed 2 state variables being the heights of the tanks in that question. Okay, so what is the idea here? The idea is to eliminate the space variable dependence. Okay, how can we do that? Well, what we can do is, instead of having a continuous x variable, we can divide the system into segments for which instead of x we assign an index. For example, I will solve an example, in fact our solid rod example with a finite element method at the end. But what's going to happen is that you divide the rod into equally spaced portions, and for each portion you treat it as if it was a lumped parameter model. That means having components interconnected together, and for each component you will basically have a lumped parameter model. So the more you divide the rod, the more finite elements you would have, and for each, because you write an equation for each one of the elements, the higher your order of the system will be, because each segment will basically have its associated differential equation. Obviously, the higher the number of elements, the more closer you are to the continuous solution, because these segments are becoming smaller and smaller, approaching an infinitesimal element that we use to derive the partial differential equation. Okay, so this finite element method is one way of dealing with partial differential equations, and what happens is that you transform that partial differential equation of a much lower order into an ordinary differential equation of much higher order. Okay, so let me write this for you. Okay, so the idea is that you divide the space variable into finite number of segments of small but finite size. Each such segment is basically modeled as a lumped parameter. You can call it a component, okay, in a higher order overall system. So assuming n segments, biriniz bayağı uykulu gözüküyor. Mikrofon da açık. İsterseniz mikrofonu kapatın. İyi durumdasınızdır umarım. So the solution of the discrete version, mind you, when I say discrete version here, we don't mean obviously discrete time, but what we mean is a discrete space. Okay, we haven't discretized the time variable, it's still a continuous time system, but we have discretized the space variable. Okay, so this discrete version uniformly approaches the PDE, partial differential equation solution, as n goes to infinity. Okay, what is the advantage of this is that we can use all our control theory methods available. What is the disadvantage is that you have often a much higher order system. Okay, so we got rid of the partial differential equation, which is a good thing, but we now have a very high order ordinary differential equation. All right. Any questions so far? Now I would like to have our quick class exercise at this point, and I had 5 questions for you, but because I'm also kind of becoming a bit lazy at this point, I want to ask 3 of those questions today and 2 of them for tomorrow. Okay, so I don't want to prepare another quiz for tomorrow. Okay, so 3 short questions, all of them true false. Let's have a break to our recording and then come back. Basically what we will do after we come back is that we will first attempt to with a number of assumptions, we will try to solve the partial differential equation to see how it can be done. But later on, we will see how we can space discretize this temperature problem, okay, the heat propagation in a solid body using the finite element method. And we will see the correspondence between the two. Usually, it's much kind of more intuitive and easier to use the finite element method to arrive at a higher order but ordinary differential equation system. Okay. Do you guys have any questions at this point? Okay. So let me switch to our